And now, when charge is moving through a conductor, current will be produced on the in the conductor. So we define current I as the rate of flow of charge, right? The unit is in unit ampere. So this is a definition of current, the rate of flow of charge. If you look at the microscopic view of a conductor, for example, if I have a conductor which is in a cylindrical shape, and I connect a conductor to an EMF, which is an electromotive force of E, right? E is called it as EMF, and on the left side of the conductor will be charged to positive. Here will be negative. So the electron in the conductor, right, will be flow from the negative polarity to the positive polarity with the drift velocity of Vd. Vd we call it as drift velocity. Drift velocity. It is the velocity of the electron in the conductor due to the electric field, right? So because the electric field will be basically induced in the conductor from positive to negative, right? This is the direction of the electric field in the conductor. So the current flow in the conductor I is equal to NAVE, where N is the number of electrons in the conductor per unit volume. A is the cross-section area of the conductor. This is A, right? Vd is the drift velocity of the electron in the conductor, and E is the charge of electron. So this is the another definition or another expression to express the I in terms of the drift velocity of the electron, right? So this expression can be derived out by using the definition of current, which is the rate of flow of charge. Right, so when we talk about this EMF, right, so EMF stands for, as I mentioned to you just now, it stands for the electromotive force. So if you look at the structure of the EMF, for example, this is my battery, right, which is EMF. And inside the battery, actually, there is one small resistor, right, with the resistance of R. Okay, so this is actually the actual voltage across the voltage, right? So the voltage across, actual voltage across the battery. So the voltage across, the actual voltage across the battery, we call it as terminal voltage, where terminal voltage is equal to EMF minus IR. I is the current flow in the circuit. Okay, so that is the terminal voltage expression. If you take into account the internal resistance exists in the battery. So ideally, the internal resistance is equal to 0. Therefore, the V terminal is equal to the EMF of the battery. Okay, now when you talk about this current, right? So basically, currents means the flow of charge. Current could be flow in a conductor when we supply an EMF to the conductor to produce a complete circuit. So basically, there are two types of current that can be produced. One, we call it as DC. DC stands for direct current. The other one, we call it as AC. AC stands for alternating current. So for direct current means the current and voltage produced is always a constant. For example, y-axis is V, or it could be I as well, right? So the current produced or the voltage for the DC is always a constant. And the x-axis here is time. So this is direct current. However, for alternating current, the current is fluctuating. Okay, for example, if I refer to the graph of V against T, right? So the graph is fluctuating, the voltage is fluctuating in a sine waveform. And the y-axis here, it could be voltage or current. And therefore, for this type of current or voltage, we can use a sine waveform to represent it, right? So for example, I'm using the expression of V equal to V naught sine omega t to represent the voltage of an AC, and current is I equal to I naught sine omega t, where omega is equal to 2 pi f. So what is I naught here? I naught here, if you refer to the graph, stand for the maximum voltage or the maximum current. Okay, and some of the reference book, they may use the peak as to represent the maximum current or the maximum voltage. Okay, so if I multiply these two terms, I will get another parameter which is called it as power, where power P is defined as the product of V and I. Okay, so since V is equal to V naught sine omega t and I is equal to I naught sine omega t, so when I multiply, I will get V naught I naught sine square omega t. So for this graph, the graph of power, it is actually a sine waveform as well, but we have to square the sine waveform where you will get this style curve. Okay, so this is the power, and x-axis will be the t, where the maximum value of the power is the product of V naught and I naught. Okay, so we can also get the average. Average of the maximum, average of the power is actually half of the V naught I naught, right? So this is average of the power. So we can also derive out what is the expression for the average power other than from the graph here is equal to half V naught I naught. So to derive it out, you can refer to this expression. Okay, so let's say I'm referring to a term called it as IRMS and VRMS. So the average power in an AC circuit is equal to IRMS multiplied with VRMS, where IRMS is equal to I maximum divided by square root of 2. However, VRMS is equal to the V maximum divided by square root of 2. Therefore, the average power for an AC source is equal to half I naught V naught. Okay, so this is for AC source power, average power for the AC, voltage for the AC, and the current for the AC. However, for DC is always a constant. So this part here belongs to AC. Now let's refer to electric circuit. For example, if I have a simple electric circuit which consists of one battery and one resistor, so we can find out what is the current flow in the circuit by using a law called it as Ohm's law. Ohm's law said that the current is proportional to the voltage, where the proportional constant is called it as resistance. All right, so Ohm's law it could be applied for either DC or AC. So this is Ohm's law. So what is resistance? So basically resistance R, okay, is proportional. R is called as a resistance, is proportional to the length and inversely proportional to the cross section area, right? So where R, the expression for R is equal to rho L over A. Rho here is called it as resistivity of a material. Resistivity of a material, which has the unit of ohm meter. Okay, the unit for resistivity is ohm meter. And the resistance value here do change with temperature. So if temperature increase, the resistance will be increased as well, where resistance R is equal to R naught 1 plus alpha T minus T naught. Okay, so T naught is the temperature. So usually we use the temperature, room temperature at 20 degrees Celsius. R naught will be the resistance at room temperature of T naught. So from this expression, we can find out what is the resistance at any value of T. Okay, same as a resistivity. Resistivity will change as well when the temperature change, where rho equal to rho naught 1 plus alpha T minus T naught. So this alpha here, we call it as temperature coefficient. Temperature coefficient. Okay, so this is a resistance. Now let's look at another term, call it as power. Okay, generally, power is defined as P is defined as energy per unit time. Okay, let's recall back. How can we relate the energy to the electric potential? So just now we have defined that electric potential is potential energy per unit charge. So potential energy here is actually referred to energy. Therefore, energy is equal to Q multiplied with V, right? Energy is equal to Q multiplied with V. So QV over time. Time is T. So if I recall back what we have learned so far, the current is defined as the rate of flow of charge. So I use the definition of current, and I also use the definition of the electric potential to derive out what is the expression for power. So from here, I know that the power is QV over T, where Q over T is referred to current, right? Q over T is equal to the current. You can use the capital letter of T or small letter of T. So eventually, power is equal to the product of VI. So that's why in a AC source, why the power is defined as a product of VI. Okay, so that is how you get the power. So this is power terms. And now we further explore resistor. So this resistor here, it could be connected in series or parallel. So we can apply Ohm's law, and by referring to the circuits connected, either the resistors are connected in series or parallel to analyze the circuit. Okay, for example, if I have a resistors connected in series, for example, I have two resistors connected in series, such as this, and with a battery, connected with a battery. Resistor, the first resistor is R1, second resistor is R2, and the current flow here, for example, is I. Okay, so since they are connected in series, so the current flow through the first resistor is same as the current flow through the second resistor, where I1 is equal to I2 is equal to I. So to get the voltage across each of the resistor, okay, let's say this is V1, this is V2. The voltage drop across each of the resistor could be find out from the law, call it as voltage divider rule, okay, voltage divider rule, where V1 is equal to R1 over R1 plus R2 multiplied with V, where V is here, total voltage across these two resistors. However, V2 is equal to R2 over R1 plus R2 multiplied with V. So if you look at here, this is 1, here will be 1, this is 2, here will be 2. So this rule, we call it as voltage divider rule. Okay. And what happens if the resistors are connected in parallel? So resistors in parallel. Okay, let's say I have two resistors connected in parallel, such as this, R1 and R2, and connected to a battery of V. For example, the voltage drop here is V2, voltage drop across the resistor 1 is V1. Since they are connected in parallel, V1 is equal to V2 is equal to V. So what happened to the current? So current flow up from the source is I. So when the current reach the branch, it will break into two. Current flow through the resistor R1 is I1, flow through resistor R2 is I2. So the current of I1 is equal to R2 divided by R1 plus R2 multiplied with I. I2 is equal to R1 divided by R1 plus R2 multiplied with I. So this is what we call it as current divider rule, right? So where this is 1, here will be 2, here is 2, this one will be 1. So this is the expression for you to get to analyze the circuit when the resistors are connected in parallel. If you have a circuit, complicated circuit, where we are unable to find out whether the resistors are connected in series or parallel. For example, I have this kind of circuit, a few sources here, right? So in this case, I do not know whether the resistor of R1, R2, and R3, they are connected in series or parallel. So what should we do? We have to apply another law. Okay, we cannot just simply apply the Ohm's law. So we have to apply another law. We call it as Kirchhoff law. Kirchhoff law. Right? So basically, there are two Kirchhoff law. One we call it as Kirchhoff current law. Another one we call it as a Kirchhoff voltage law. Kirchhoff current law states that at a junction, summation of I is equal to 0. However, Kirchhoff voltage law states that in a closed loop, the summation of the V is equal to 0, or you can write it as the summation of all the EMF is equal to the summation of the potential difference across each of the components, which is IR. Okay, so this is Kirchhoff law.